And it's my pleasure to introduce for the first lecture of this series, Joaquin Rodriguez-Nieva. So actually, Joaquin comes originally from Argentina, and he moved to the US a long time ago when he was young, and he had an almost ideal career, so he spent all his time at Ivy League. He did a PhD at MIT, and then went for a postdoc at Harvard, got independent fellowship in Stanford, and right after that, he got hired by Texas A&M to reforge or refound the condensed matter theory research at that department. So he has an important mission, and this is possible because Joaquin is a researcher that spans interest and expertise over a very broad spectrum of topics. So he could pass from material science, and in particular graphene, up to hydrodynamics and non-ergodic quantum systems. That is what he's specializing right on in his assistant professorship career, encompassing hydrodynamics and quantum sensing. And he will give an angle on emergent non-equilibrium phenomena that is somehow complementary to what Sebastian has presented. So it's more isolated system, there is no drive, there is no dissipation, still the system stays far away from equilibrium. Originally was meant to be complementary to another lecturer from Mainz that would have talked also about magnetic systems. I guess most of Joaquin's lecture will be about spin systems. So also here in Sao Paulo, you hold the entire weight of condensed matter, of hard condensed matter theory, as you do in Texas. So you have the floor. Thanks so much for coming here with us.
Thank you, Jamir, for the very kind introduction. I got it. I can put it. You need it? Okay. Right, so let me start with a broad introduction to set the stage and to put you all in the right frame of mind for my next 3 lectures. So let me start by reminding you essentially what is our main goals as condensed matter theorists. Particularly here, there are lecturers also in AMO. So traditionally, one of the main goals of condensed matter physics has been characterizing thermal phases of matter, particularly at low temperatures. So here there are 2 keywords. The first one is temperature. That essentially means that the system is at equilibrium, thermal equilibrium, so it's contacted with a bath. It's contacted with a heat bath that fixes the temperature of the system. And the second keyword is low temperatures. So that essentially means that if I have, for example, a many-body Hamiltonian, and I were to plot all the eigenstates, all the eigenvalues of the Hamiltonian, and I plot the density of states, so I fix a window, and I count how many states I have in all these windows. What in condensed matter physics, traditionally, we look at the very tails of the spectrum, essentially at the ground state properties, or at very close to ground state properties. And usually, very close to the ground state, what we have is a few number of quasi-particles. And the thermodynamic properties are described only by, let's say, a small density of quasi-particles. So to give you a concrete example, let's grab a paradigmatic case of symmetry breaking. For example, I have a spin system, and I am an experimentalist. I can tune temperature and, for example, some field, like a magnetic field. The system can go through a phase transition. So, for example, for some low enough temperatures, all the spins will want to align, and I will form a ferromagnet. For other parameters, all the spins will want to be independent from each other. I will be in a paramagnetic phase. Usually what we do is we understand the properties of the system, the static or dynamical properties of the system within linear response. So that what essentially means is that I come with a field and I tickle the material very lightly. So I excite a few number of quasi-particles, and I see how the material responds to that perturbation. So that's within linear response. And already at thermodynamic equilibrium, we have a lot of paradigms. I already mentioned ferromagnetics or antiferromagnets, which is symmetry breaking. We have superconductors, which is another form of symmetry breaking. We have topological systems, we have Fermi liquid theory, and so on. And in understanding all these systems, the notion of universality is very important. In particular, we tend to categorize or group all systems independently of the microscopic degrees of freedom into universality classes, which share the same type of low energy excitation and thermodynamic properties. To give you a concrete example, for example, an antiferromagnet and superfluid helium, they share very similar low energy properties. So that's, we say that they have a very similar universal behavior. The same is true for example, semiconductors, which are at low doping. Or we can talk about the metals or heavy fermions. They are all described within Fermi liquid theory and so on. So in the last couple of decades, I would say, there has been remarkable progress in condensed matter physics, particularly driven by experiments. And you have been hearing about these experiments this morning and also last week with Derek, where we can drive quantum systems to regimes where all the traditional formulations that we use to understand thermal phases of matter break down. To give you some concrete examples, for example, in pumped spectroscopy, one shines light to a system, one creates a large energy state, which then one probes with a second pulse, a non-equilibrium state. In cold atomic gases, one can essentially isolate the system and evolve the system through unitary dynamics. We have NB centers in diamond, which are ensembles of spins. And more recently, we have quantum simulations in noisy intermediate scale quantum devices, which are, of course, they are not perfect. They have noise, but sometimes for a condensed matter theorist, the noise can be a feature rather than a bug. And the key distinction is that now, one is no longer talking about very low energy properties. One is not talking about ground state properties. It's not hard to even initialize a system which is right in the middle of the spectrum. So one can essentially explore the entire phase space, until, at least in principle. And as a condensed matter physicist, the first thing that comes to mind is there are two key challenges or two questions that arise. The first question is, okay, what are the relevant degrees of freedom that are relevant? In particular, now we are talking about multiple scales, multiple energy and length scales, and identifying which are the relevant degrees of freedom across the entire phase space is not particularly easy. And more generally, one can ask a more general question is whether there is anything universal about far from equilibrium regime. Yeah.
So would you mind expanding on, like, what do you mean by universal properties, like what concretely they might be?
Universal properties. So in the context of non-equilibrium systems, it means properties that do not depend on details of so usually universal means independent of details of the Hamiltonian, but also in the context of far from equilibrium, it also means independent of initial conditions. So you can start the system from a highly excited state, and it won't care too much about details of the initial condition. It will care about some coarse, like for example, the energy or number of particles that you start the system with, but it won't care about details of the initial state. So it's kind of like the same meaning as thermal and at equilibrium, with the distinction that there's also an additional condition, which is independence of initial conditions.
Okay, cool, thanks.
Yeah. Okay, so that's as far as the slides go. So essentially, what I will try to give you is somehow my own perspective on specific examples of how, specifically as you ask, how universality can arise in many body systems. So I will, is there something to, Okay. Do I need to turn off the Zoom? Or no, do I have to if I start, right? No, okay. Okay. So as Jamir already pointed out, to set the stage and now to narrow down to the kind of systems that I will be considering, the first key ingredient is I would be talking about isolated systems. So this essentially will set my lecture completely apart from this morning by Sebastian. So now there's no drive. So essentially the situation you have to think about it is a many-body system where you initialize the system. For example, you pump the system at time 0. And at time 0, you essentially isolate the system and you let it evolve through its own internal dynamics. So there's no drive or dissipation. Of course, it's many-body, so there would be interactions, there would be emergent phenomena out in this arising from dynamics. And the key word now is that it will also be prethermal. So this essentially means that I will be considering systems which, in principle, at long times or at infinite times, they would reach thermodynamic equilibrium. But in some long-lived prethermal regime, there could be some, the system may get stuck in some intermediate time, but still long-lived prethermal regimes where the properties of the system will be very different, or the properties of correlation functions would be very different from what you would expect at thermal equilibrium. So far, so good? So yeah. There's a question.
Okay, so I wanted to ask you about prethermal.
Yeah.
If you could clarify the difference between transient behavior and prethermal.
Well, prethermal, in a sense, it's, well, transient, in principle, they could have similar connotations, but prethermal, it means that eventually you will get to thermalization, so it's still a thermal state. Transient probably is more generic, but in the context of what I'm talking, especially I'm talking about systems which is a transient state, which would, prior to equilibration. Yeah. So the general expectation, so if you grab a typical, if you grab a statistical mechanics textbook and I ask you how does a system which is many-body and thermalizing would relax to equilibrium, the usual figure that you would look or you would find is that if I'm looking at some observable and I start from an equilibrium state, eventually you will reach at some time scale tau star, which is usually called the relaxation time approximation. You will usually expect some featureless type of thermalization where here at long times, the expectation value of the observable would be described by thermal Gibbs ensemble. The exception would be, for example, if this operator has some overlap with the conserved charge, you would expect some diffusive scaling, so some simple power law scaling, but generally you would expect something more generic. But it could happen also that systems can get stuck in some sort of prethermal regime, so the figure that you would expect is that there's some sort of metastable state where prior to reach equilibration, you will get stuck in this regime and you will inherit the properties of this prethermal regime prior to reaching thermodynamic equilibrium. So now the first question that I wanted to roughly, or I wanted to somehow categorize, and maybe you can, maybe we can do it as an exercise. So when I ask you what are the processes that could generally constrain thermalization, so what are the basic constraints that systems have that constrain thermalization? Well, that's good. That's one process. So integrability, basically, you mean in general symmetries. integrability, you have a macroscopic number of symmetries. It's not the only way that you can constrain or you can arrest thermalization. But let's start somehow classifying. So essentially, the question I will ask is the following: let's ask the question about, okay, how do symmetries and how, in general, it's like in thermal equilibrium, you have symmetries and dimensionality. So you can ask the question of how symmetries and dimensionality could prevent the system from thermalizing. When you talk about ground state properties, you ask a different question. You ask us of what symmetries the ground state is breaking. So usually you characterize all the thermal phases of matter or the transitions between them in terms of the symmetries that get broken. But in far from equilibrium, you can ask how do symmetries prevent the system from thermalizing. So let's make a map that I will be using throughout my lectures. So for example, one way in which you can arrest thermalization is if you have, let's assume I quench a system. I start from an initial state that has energy below a critical temperature, so below some ordering transition. One way in which arrested thermalization can occur is through an ordering field, order parameter. Actually, can you read here at the back? Is it good enough? Okay. So for example, let's assume that I have a system that, let's go back to the example that I already gave. Let's assume I have a magnet. And I quench the system below the critical temperature. So the simplest process that could prevent the system from thermalizing is coarsening dynamics. So in this example, for example, what would happen is that if I quench below the critical temperature, there would be regions where the spins will want to align in one direction. Maybe there would be another region where spins will want to align in the opposite direction. And then dynamics will no longer be governed by the properties of bulk excitations. What they would be governed is by how these interfaces between domains compete with each other. So for example, if you have a three-dimensional magnet, you will see islands of magnetization. So these islands will start growing according to coarsening laws. If you want to compute, for example, the expectation values of spin-spin correlation functions, those correlation functions will not be governed by what we would naively expect from spin wave theory, but you will be governed by essentially the dynamics of domain walls. So far, so good. So this is one trivial or one well-studied example in which essentially ordering will prevent thermalization or will slow down thermalization. A related example, for example, would be aging. So when you have aging, you essentially, and now imagine that you start from an initial condition, a generic initial condition, but the energy of the initial condition is such that you are exactly at the critical energy or at the critical temperature. So in that case, the system is at criticality. And from what you know from thermal equilibrium is that, for example, correlation functions will acquire some power law. Some long-range order, there would be fluctuations of the order parameter at all scales. There would be dynamical slowing down. And then the scale that controls how fast you reach thermalization is how close you are to the critical energy. So far, so good. So now let's assume I start from an initial condition, which is in principle at infinite energy. So it's very high energy, so there's no ordering parameter, so there's no tendency of the system to break a symmetry. So now the only constraint that I have on my system is conservation laws. So somebody already mentioned what would be the mechanisms that prevent thermalization is integrability in this case. So if you have So everybody is familiar with integrability? Oh, yeah.
Okay. About coarsening, does it mean if you have a quench across a transition, this is the situation where this occurs generally? I didn't understand.
So, well, yes, essentially you can think about, depends what are you thinking about. For example, that you quench the Hamiltonian, so you change the Hamiltonian parameter, so you start from an initial condition. It could be either or, right? You can start from an initial condition, which is, for example, a product state, so there's no correlations, and the energy of the initial condition is below the coarsening transition. So in that case, when you evolve the system, there will be regions where spins will tend to align in one direction and spins will tend to align in the opposite direction. But it could also be the case that you're thinking about where you start from a simple state and you quench the Hamiltonian, you change the parameter of the Hamiltonian. So it doesn't matter, it's either or. Again, this goes back to the question I was asked before. It doesn't really matter how you initialize the system. It will always govern a long-lived prethermal regime independently of where you started from.
Thank you.
So the second case, good integrability. So as somebody already mentioned, so in integrability, you have too many conservation laws, so you have an extensive number of conservation laws, so as many as particles that are in the system. And then this essentially prevents the system from exploring the whole phase space. If you are close to an integrable point, so essentially integrable points are very fine-tuned points in phase space, basically in Hamiltonian parameter space. So they are very fine-tuned points, but if you are very close to an integrable point, then the scale that governs thermalization is this integrability breaking parameter in the Hamiltonian. And again, this would be true even if you're at infinite temperature. So even if you're at infinite temperature at very large scales, if you start from an initial state, which is right in the middle of the spectrum, this would also prevent thermalization. Yeah.
I'm sorry, it's still about coarsening.
Yeah.
But essentially should be an initial condition so that you have quasi-particles produced just locally effectively, so that it is not a global quench that immediately makes everything thermalize. I'm trying to imagine, because from the example that you were portraying, that dynamics occurs at the interface of domain walls. It's kind of effectively is local, the dynamics. Is this the source of this coarsening? Just to have a more...
What you mean local, you mean that the domain walls?
Like it's just at the interface.
Yeah, exactly. Think about it that there's, let me change the wording. There's a new degree of freedom that is not apparent in the ground state. So it's not just spin flip excitation, it's just the physics of domain walls that is governing dynamics. So now the relevant degrees of freedom are topological defects. So there's a qualitative change on the relevant degrees of freedom.
Thank you. Sorry for...
No, all the questions. So there's no rush. You can interrupt me as much as you want. Okay, so let's assume that there's also, so again, we are at very large energies. Even if you don't have integrability, you can have processes in which conservation laws still, let's say, slow down thermalization, and this goes into the general, what I would call, very broadly, turbulence, which could be a hydrodynamic turbulence, or also it's called wave turbulence. Or wave turbulence. Also in the literature, it appears, it's connected, you probably have heard the name non-thermal fixed points. Which is something very similar. I will explain it in a few minutes, what this means. This was a name that was coined by Burgess at Heidelberg, I think in 08. And basically, I will be discussing examples where all these processes show up. Then let me just mention there's one additional case, which I will not consider it as a rested thermalization, but I will also consider it in the last lecture. Which is there's another regime where an isolated system can still exhibit some non-trivial dynamics, some universal scaling, which is instabilities. And here what instabilities means, I mean as some sort of dramatic instabilities where the system may be at thermal equilibrium. There could be very tiny thermal fluctuations, but the system would be unstable to nonlinearities. And those nonlinearities will govern the prethermal regime. Probably the paradigmatic case is the KPZ universality class, which is essentially hydrodynamics in one dimension. So in one dimension, fluctuations are very relevant, and these nonlinearities will govern scaling. In the last lecture, I will give an example of a different universality class, different from KPZ in higher dimensions. But at least this is how I like to think about problems of trying to categorize, okay, which is the mechanisms that slow down thermalization, or put them into different putting them into different categories. So usually when you talk about arresting thermalization, the picture that you usually see so usually the pictorial way is that if this is the thermal state, oh, thank you. And this is my initial state. As the system approaches the thermal state, it will get stuck into the proximity of what's called this non-thermal fixed point. This is the way it's called, it was initially called by Burgess. And in this prethermal regime, what you are looking for, and what we will be looking for in these lectures is, for example, the scaling. So for example, if I'm looking at equal time correlation functions, we will look at universal scaling of simple observables. For example, if we look at density-density correlation functions or velocity-velocity correlation functions, we will look at scaling forms and argue that the scaling exponents that arise in these correlation functions are universal. So again, they are independent of initial conditions, and we will use different approaches to compute these scaling exponents and these universal scaling functions. Yeah.
But do those non-thermal fixed points depend on the initial condition, in a sense of from some initial conditions you won't get trapped there, or it is like a like a global attractor in a sense?
It depends on initial conditions in the sense of the on let's say very coarsely in terms of energy and number of particles that you initialize the system with. But it doesn't matter in terms of details of the initial conditions. So all these relative phases or something more, it won't depend. Let's put it this way: it doesn't matter in terms of details of the initial condition, but it matters on just global constraints in terms of symmetries. So basically, energy, particle number, momentum maybe of the initial condition, so on.
Okay, and given the Hamiltonian, like coming back to this classification here, like how can I know within which universality class it should like fall into? Like,
yeah.
Because okay, I might know that my Hamiltonian is like integrable or something, right? But then for the ordering parameter, like I would have no idea. Perhaps like Ising model or something like gets into like this coarsening, and perhaps like some other models like which are for which we know like we I don't know, we're close to a critical point with an initial condition, like they would exhibit this like aging or something. But like, how can I know?
Yeah, well, that would be the main point of my talk in a sense. So even the same Hamiltonian could have different ways in which it can relax. So there could be different types of relevant degrees of freedom, and that's exactly what we will be discussing. Depending on which relevant degree of freedom is dominating, that you could enter different regimes. And even, and this could be governed both temporal, so temporal-wise, there could be different steps of thermalization. And even if you look at different length scales, there could be different relevant degrees of freedom, different scaling exponents, and so on. So that's kind of the key take-home of my talk, is that it's not like a thermal equilibrium where you have very small density of quasi-particles, and that's basically it. In this case, there's no such thing as one thermal pathway to equilibration. There are potentially multiple thermal pathways of equilibration.
Cool.
And that
Looking
would
forward.
be one.
Thanks.
And again, so going back to that question, so essentially the goal of these lectures would be first to describe a universality in these prethermal regimes. So I will use several approaches. So something that to keep in mind as a heads up, so in all the cases I will be discussing, there would be an emergent classical theory that describes this prethermal regime. And the fact that there's a classical theory should not be surprising, because usually when you are at high energies, all these quantum phases wash away, and essentially you will have a description in terms of a smaller number of classical degrees of freedom. Probably the only counterexample to that, I would say, is probably many-body localization, for example, where you have an emergent integrability in terms of local conservation laws, and in that case, there wouldn't be an emergent classical description. You have a lot of phases that are important to describe, in that sense, the absence of thermalization. But in all the cases I will be discussing, there would always be some emergent classical description. As I mentioned, the take-home message, one, I just said it, I was asked about it, is essentially there would be many possible pathways of relaxation. And I will also be discussing several approaches to describe universality. So some of them are analytical. So I will be talking about kinetic theory, which is the kinetic theory. I will be talking about hydrodynamics. I will also be talking about scaling in the sense of RG type of scaling. And then I will also, if there's time, I will also talk about numerical approaches, such as truncated Wigner approximation, which is a numerical way to study these prethermal regimes. Okay, any questions about the introduction? So this would be kind of the mindset that you have to keep in mind for the next lectures. So now we can start thinking about a concrete example. Okay, we can go here. So I will use, so just to start with the question I was asked about, what are the relevant degrees of freedom? Let's consider the simplest case before we talk about spin system, or I also will talk about hydrodynamics. Let's talk about a Bose gas in the dimensions. So this is so again, this, I assume most of you at some point in your career, you probably saw Bose gases at least at thermal equilibrium. Also, Sebastian was talking this morning about, it's a very simple example. Well, I wouldn't say it's simple, it's one of the most well-studied examples since the realization of Bose-Einstein condensate. I think it was probably 20, 25 years ago now. During the early 2000s, there was a lot of work on understanding both equilibrium and non-equilibrium properties of Bose gases. So now we can start asking, in this simple case, just to apply the framework, or to apply the framework that I just described, we can start asking, okay, what are the possible regimes, depending on how I initialize the system, and what are the possible relevant degrees of freedom that can arise as the system reaches a thermodynamic equilibrium. Okay, so the simplest, let's start with case one. So let's assume I have a Bose gas, and it's initially at 0 temperature. Let's assume at time 0, I pump, I drive the system. Like I push all the particles to some high energy, so I create a delta function at high energies. And I asked the question, okay, how does the system approaches equilibration? Or let's not do it. Let's not do any calculation. Let's just do it more. Let's verbalize it, how it would happen. So the idea is that if energy density that you inject in the system is sufficiently large, essentially what you would expect at sufficiently large temperatures is that you would get a low-density gas of bosons interacting with two-body collisions. Basically, this would start, let's say, changing shape. It will start looking more like a thermal distribution. But eventually, at very long times, what you would get is something more like a classical gas of particles weakly interacting with each other. You can use even molecular dynamics to describe it. The system, your energy is large, and here, let's say large compared to the critical temperature of the Bose gas. You can describe it with kinetic theory, which is what I will do in around 10 minutes. But the expectation would be that if the density is sufficiently large, you will get a weakly interacting Bose gas at sufficiently long times once the details of the initial condition gets washed away. So here I would call it a non-generic regime where there's dephasing. And this I will describe with kinetic theory in a bit. Let's assume that now energy is large, but not quite. Let's assume that I quench it, that I initialize the system, but the energy density is not sufficiently large. So what would you expect in a Bose gas, for example, in 3 dimensions, if energy is not large? What would happen at sufficiently long times? So once particles start cascading down in energy, anyone wants to guess? Yeah, exactly. So at low energy, so if the energy density is not sufficiently large, once particles start redistributing, a lot of particles will start condensing at low energies. So now you will see, so this is if energy is less than critical energy. So now there would be a second step, which would be condensation. In other words, there would be an order parameter. So now the field will acquire some expectation value. And now this picture of weakly interacting Bose gas breaks down because now you have a condensate. Essentially, your particles can also interact with the condensate through 3-body collisions. They could kick particles out of the condensate and so on. So you need to, let's say, rewrite or rewrite the theory in terms of having a condensate background. Sorry, actually, people there can see. On the yeah. It's good, yeah. So qualitatively, you will see that if once particles start trickling down, you will enter into a second different regime where there's a condensate. So now you see that there's a second step of thermalization, and actually there is a third case, or a third potential regime that could arise. Can anyone guess? Once particles condense. Let me actually just give you a hint. What happens if I have a condensate and I make it spin? I give kinetic energy through spinning a condensate. Yeah, right. So you can start forming topological defects. So if I initialize my system such that it has a vorticity, you can also form a network of vortices, which are the topological defects of the condensate, and you could potentially enter a third regime in time, or there will be a new length scale in the problem, which is the distance between vortices. So this kind of answers your question of there's no just one way in which the system would thermalize. There would be potentially many different degrees of freedom that could govern thermalization, and each one will be characterized by its own dynamics and its own scale. So there would be multiple scales, energy scales and length scales in the system. So far, so good? Yeah. Okay, so now we can start doing something more, some calculation. Actually, I will leave this. So now let's focus on the first regime, which is, essentially the physical picture that you should have in mind is I initialize the system, I quench the system such that all my particles are at some high energy. As I said, here the energy density is so large that essentially the system behaves like a weakly interacting Bose-Gas, so kinetic energy is it's larger than interactions. So what I will write is a kinetic theory of these quasi-particles, of these Bose particles. So is everyone familiar with kinetic theory? Okay, so maybe let me just walk you through the calculation. So usually in kinetic theory, what you assume is that you eliminate all relative phases between degrees of freedom. So what I will assume is that in my initial state, there would be an initial state where, regardless of how you initialize it, there would be a dephasing. So all the relative phases between the bosonic operators will vanish, will wash away. There's random phase approximation. So the 2-point correlation functions will be delta functions. So this will only be non-trivial if k equals p. I will also assume that there's no ordering, or there's no condensation, so the expectation value of a bosonic operator will always be 0. And the same, of course, happens for if you have two correlation for two creation or two destruction operators at any momentum. And then the key idea of kinetic theory is to write the time evolution of the distribution function of particles. So if you never did the calculation, roughly the way it goes, so you have to take the derivative of the density function. Also, there is the macroscopic equations of motion that comes from the Hamiltonian. In momentum space would look. They will have a linear term, which is the frequency, which is the k-squared dependence or dispersion of the bosonic particles. Then I will have a kinetic term, a collision term. So essentially here you take time derivative of the first operator, you plug in the equation of motion, the macroscopic equations of motion of the first operator, and the same for the complex conjugate. What you will find is that, sorry, here I'm missing an I sign because of the I, the complex, because here you have complex numbers, this term will vanish out because you will acquire an overall minus sign. So you will get a plus minus omega k density operators. So the leading order term on the right-hand side would be a 4-point. Let me just write it symbolically such that I don't have to write all the sums. You will get expectation value of 4-point correlation functions. What you can show, there's also an I, an imaginary. So what you can show is that this term will average to 0 if you assume random phase approximation. Essentially, this will not contribute to the equations of motion. So then what you have to do is a perturbation theory, look for resonant processes in terms of this creation and annihilation operator. So you will get a 6th order correlation function where you will get the usual kinetic theory. Let me just write it down. So you have to do Fermi-Golden's rule. So you will get some. So let me just walk you through, if you've never seen kinetic theory, essentially what you will get is Fermi-Golden's rule. So this includes energy conservation of so essentially you have processes. So the rate of change of particles in a mode K. So essentially you will have processes that you have, for example, a particle with momentum K1 and K2. They will interact and it will add a new particle into state K. You need to have momentum conservation, so this applies. And then what you would have is the occupation number of the incoming particles. You get a one term which appears when you do the commutation. You consider bosonic commutation relations once you do the right ordering of all operators. But essentially what this essentially is telling you is a balance equation between the number, the rate in which particles are falling into level K, minus the rate in which particles are going out of level K through interactions, through two-body collisions. And essentially this initial term is nothing else than Fermi-Golden's rule. So there's energy conservation and momentum conservation. So if you have never seen it, on Thursday when during the lecture or the tutorial, we can go through the details if you're interested, but this is as far as what we will need for the lecture today. Again, this is a balance equation of what's coming into level K and what's coming out of level K, or energy state K. Oh, yeah.
So I'm sorry, how did you get this Schrödinger's equation in that case? Like, how can I see it immediately?
This equation?
Yeah.
Oh, well, this is the equation of motion of operator psi, starting from the Hamiltonian.
Oh, so that's for this particular Hamiltonian.
Yes, so here I'm always talking about the Bose-Gas.
Okay,
right?
okay, cool. I see, thanks.
And here, of course, I took the liberty of just writing it in momentum space. But again, the key idea of kinetic theory is write this equation of motion, go through all the calculations by writing the microscopic equation of motion, use this assumption of random phase approximation, and of course, once the dust settles, you will get Fermi-Golden's rule, counting number of states coming into state K and transition rate into state K minus transition rate out of level K. Again, and this is already a closed equation because once you know the initial density, yeah.
Sorry, but why the kinetic term is absent? The omega k, the term proportional to omega k in the equation of motions of MK?
Right, because there's a complex number. So here, when you take derivative, so you will have a derivative of psi k plus derivative of psi k. Let me just write it. So you will get two terms.
Okay.
And then you will have a second term. So the quadratic term, this one will give you omega k psi psi, and then this one, you have the complex conjugate, so this will give you a minus sign, and then you will cancel out.
Thank you.
Yeah. Okay, so this is very generic. Again, once you know what's the initial condition, I can literally put it on a computer, put the density at some time t. This will give me how all the levels will change as a function of t. In principle, I can solve it numerically. There's no mystery. And the first question that I will ask is, what's the steady state solution of kinetic theory? So let's assume I give you kinetic theory, and I ask you what is the solution that gives you a steady state. So there's no rate of change of particle number. Who wants to propose a solution? There's one solution which is actually very simple. In fact, well, let's put it this way. First of all, the thermal solution. If I assume thermal equilibrium, you would hope at least, that if I plot a thermal distribution for n of k, this is a steady state. Thermal equilibrium should be a steady state. And in fact, you can show that if you put the Bose-Einstein distribution into the right-hand side, into the collision term, this will give you 0. So the collision integral for the Bose-Einstein distribution is essentially 0. And this gives you a steady state. So this is one steady state. What probably, and this is very standard if you go to a StatMech textbook and you go through microscopic derivations, you will always find that, for example, if I have a classical gas, you will not have this once, and if you plug in the Boltzmann distribution, you will also get a steady state. It's the thermal distribution of a classical gas. If you have fermions, you will have a 1 minus n of k, and you put the Fermi-Dirac distribution, you will get 0. So now what usually you don't learn in statistical mechanics is that there are other solutions to kinetic theory, which are also steady states, which are steady state solutions, but they are non-thermal solutions. And these solutions acquire some power law. Note that now it's not an exponential tails, they have power law, so they behave kind of critical. And in the context of kinetic theory, these solutions were studied by Sakharov a while ago, where he found exactly analytically, so you can prove it mathematically, that there are solutions which have this form, that when you plug it into kinetic theory, they give you essentially a steady state. Let me give you some intuition, and this goes also, this is what goes under the name of turbulence. Let me give you some intuition about how this power law solution arise. So let's assume I have a fluid. So let's forget for a minute the Bose gas. So let's go through a more simple example. Let's assume I have a bucket of water, and I have a paddle of size L. So this is just water, just a conventional fluid, and I start steering the system with increasingly larger energy. So I start steering very harshly. And I could perfectly ask you the question of what's the velocity-velocity correlation function for all wave vectors. So what you will see is that when you start pumping energy into the system, there would be a characteristic wave vector, which is where you are pumping energy. There would be kind of like a peak. But then that energy cannot just disappear, cannot be dissipated very rapidly. So what would happen is that energy would start being transported across many scales. So there would be a constant flux of energy at all wave vectors, where energy will start being dissipated at smaller and smaller length scales, until at some point you reach a microscopic scale, which in the context of a fluid is basically the dissipative, the viscosity of the fluid defines this term, and where eventually all this flux of energy will get dissipated to all other degrees of freedom. So essentially there is a very wide length scale from the energy in which you pump from the length scale from where you pump energy to the length scale where that energy gets dissipated. And in this intermediate regime, you get a universal power law. So essentially the velocity-velocity correlation functions acquire some universal scaling, which in the context of hydrodynamic is 5/3. You can imagine that this argument was done by Kolmogorov in the 40s in the context of, again, hydrodynamic turbulence. But you can essentially apply exactly the same arguments to a kinetic theory of weakly interacting waves. So you can use exactly the same logic. So imagine that let's assume this is my wave vector. Actually, let's do it this way. let's assume that, for example, I start pumping particles, I start injecting particles at high energy, and I start withdrawing particles at very low energy. And let's assume that these scales, I can make them mathematically very far apart from each other. So in this intermediate regime, you will get a power law where particles will be cascading at lower and lower energies until you reach the scale in which you are extracting particles. So you will get a universal power law associated to the particle cascade. Or alternatively, I can do the same experiment with energy. For example, I pump energy at very low wave vectors, and that energy will be cascading at very larger wave vectors with another power law. And what you can show is that these solutions are steady-state solutions of kinetic theory with universal exponents. I will describe in a bit these universal exponents, but the important thing is that these are exact solutions of kinetic theory in the context that were found by Sakharov. And now the first thing that you can do, or probably at this point you should complain, because at the beginning of my lecture I said that I would be considering isolated systems. And now I'm considering a situation where I'm actually pumping energy or pumping particles at different scales. So somehow it seems that I'm cheating because I promised that I will only talk about isolated. But it turns out that these universal power laws can also be observed in some prethermal regime of an isolated systems. And usually the picture that you should have in mind is, let's assume that I initialize my system with some peak as some characteristic wave vector. So again, the system has to dissipate energy and has to redistribute charge in such a way that you eventually evolve to a thermal state. So what would happen from this initial condition is that there would be a cascade of particles at lower energy. So you will acquire a universal power law in the infrared. You will observe a power law which is associated to this cascade. It's called an inverse cascade because usually particles will flow to lower and lower momenta. At higher energies, you will see another power law because energies will try to flow towards the UV. You need to form the thermal tails of the distribution. And in a long-link prethermal regime, you will observe these two universal power laws, even though at very long times you will reach eventually the thermal state. So what characterizes, or what's constraining thermalization is the speed at which you can relax or you can redistribute particles across all different scales, and the same at the way you can relax particles at all different energies. Is this clear? Yeah. So a different way to see, okay, so maybe let me go a little bit, elaborate a little bit more of why you see two power laws. Usually if you compute the, let's say, the expectation or the weight of the energy operator, because energies of particles scale as k squared, usually most of the spectral weight of energy is towards the ultraviolet, whereas because particle number essentially has only this dimensional factor. Most of the spectral weight of the particle number in momentum space is concentrated in the infrared. So usually, very generically, if you initialize a Bose gas at some, let's say, some wave vector k, you will see two cascades, and each cascade will be characterized by its own scaling exponents. Let's see. Actually, let me give you the numbers. Okay, so now let me. Again, this is now it's already textbook materials. You can find it. There are very good textbooks One is by Sakharov, Lvov, and Falkovich. There's also Nazarenko. So they have you can always find tabulated in these books, for example, depending on what's the microscopic model, what are the interactions, what are the linear and nonlinear terms, you can find what are generically the scaling exponents. So for example, in the context of a system with two-body collisions, right, so let me go back to kinetic theory. So let's ask a question. What are the parameters that can, what are the relevant parameters, or what are the parameters that these power laws, nu n and nu e, can depend on? If I look at kinetic theory, the only input that kinetic theory has is the dispersion of quasi-particles. So I will call it gamma 1. So for example, in the context of Bose gas, gamma 1 equals 2. The second parameter that I have in kinetic theory is the scaling of the interaction term. In this case, it's a hardcore interaction, so it's k to the gamma 2, where gamma 2 is 0. And the last parameter that I have is dimensionality. So here, in principle, I can replace this sum by a d-dimensional integral. So in other words, these power laws can only depend on those three parameters. And specifically, they acquire a simple form. So again, depending on the dimensionality of the model, you can plug in, so for gamma 2, you plug in a 0, because it's a hardcore collisions. For gamma 1, you plug in a 2, and you can find what are the power laws that you would see in an experiment, either a real experiment or a numerical experiment. Any questions? Oh, yeah, 2 questions, actually.
I have the microphone, I go first. About the kinetic equation,
yeah.
Because the classical one, I know that at least in the textbooks, they always say that the unique solution is the Maxwell-Boltzmann distribution, for instance, if you have free particles that are interacting via collisions. Therefore, these additional solutions is present also there, or does it appear because you have in the calculations in between some kind of quantum correlations that gives rise to additional terms, and so?
Good. Actually, I forgot to make a clarification. So actually, the solutions appears when one of these terms are dominant. So for example, these solutions are true when occupancies are large. So you pump a large number of particles, these n are much larger than 1, so you forget about these quantum correlations. So in reality, well, I don't know what you mean specifically by quantum correlations, but at least this one won't be that relevant.
What I mean is, for instance, you have their expectation values of 4-point functions. And maybe in the course of the second-order perturbation theory, there are some, I don't know, some commutators that gives rise to additional terms, because the point is, in the classical regime, like in the classical kinetic equation, I didn't know of this additional solution, and so I was wondering, so it means there could be that like the system does not tend to Maxwell-Boltzmann, for instance, or Boltzmann distribution, but to this additional solution of a one power law solution. I mean, the fact that you have 2 solutions, it's a little bit, I mean, because in the classical textbooks, I didn't find it, for instance, in the classical regime. And I was wondering if, again, this solution is due to quantum effects in some regard.
No. It's not. It's about. Okay, so let me first clarify. So something it's true I forgot to mention is these solutions are semi-classical in the sense that the occupancies of the levels nk is much larger than 1. So let's forget about this one. So let's assume that now this is classical kinetic theory. So you have n cubed terms. So if you plug in the Boltzmann solution, so basically if you put the Boltzmann equation or the Boltzmann distribution, you will get 0. But these prethermal solutions or these power law solutions arise when you are actually driving the system. So the difference is that the solutions arise, you need to have some source and drain of particles or energies for these solutions to be mathematically correct or to be mathematically exact. But if you don't have a source and a drain, these solutions become some sort of artifact of a prethermal regime, which will arise in some intermediate scale window, but eventually they will evolve towards a Bose-Einstein, the Boltzmann distribution.
But so should I imagine like an additional pump term, like a term linear in the psi dag, I don't know, something like this? Or,
like
for
here?
instance, this pump of a certain momentum that can give rise to. I mean, is there a modification of this kinetic equation for this additional pump, so that we have this new solution?
No, so the way the proof goes is, okay, so you need to do complex analysis, basically a Sakharov transformation. So it's not something trivial, but you have to assume that the scales in which, so basically you have to, for example, if you are thinking about particle cascade, you have to assume that the energy in which, or the scale or the wave vector in which you are pumping particles into the system tends to infinity, and the scale in which you drain particles from the system goes to 0. So there's what's called the inertial window, which is very wide. And in this inertial window, you can show that you converge to this power law solution. So basically what you have is, the key idea that you have is that you have to assume that at all wave vectors that you have a constant flux of energy, regardless of what scales you are looking at into the system.
Thank you.
So I'm not sure, like, how should I look at those plots? Like, is it that, because like there's a time dependence to this problem, right? Like, initially I start like being localized close to this like 1/L, and then like, should I look at those plots on, say, like the board out there, like as equilibrium plots, like stationary plots, or
These
like
ones?
yeah, like
so these ones are stationary. So yes, so basically these are steady state
Okay.
solutions. So the mathematically, so the regions. So when you essentially impose stationarity, essentially these are steady state solutions, assuming that you have a drive and a drain. But again, even if it's isolated, you can still see these solutions for some intermediate scale.
And those are the ones which have like this universal power law to them.
Exactly. So
Okay,
basically
cool.
these exponents, it doesn't really matter how you initialize the system. It doesn't matter about the details of the phases, or so long as you pump enough particles at larger energies, these do not, so here you have no dependence on initial conditions. So this is just very generic about the dispersion of quasi-particles and interactions. So there's nothing else. So it only cares about very fine features of the Hamiltonian. I think about it that I could have started from a much more complex Hamiltonian on a lattice or whatever, and eventually what you would care is what happens at longer wave vectors. So let's say the coarse grain picture, or basically the leading order contributions to the dispersion and interactions. So it's very, there's no details of initial condition arising here. Yeah.
Just very fast, do they see these kind of scalings in experiments?
Yeah,
Well, they can see it?
I will show a couple of slides in a few minutes. So this is as far, another question or no? So this is as far as the power law scaling is concerned. One may also wonder about how to find the spatial temporal scaling if you are in a prethermal regime. So again, if I think about the situation in which I'm quenching the system, and I look, for example, at the distribution function as a function of time, and the system is isolated, so I'm not really driving the system. So what you would expect is that the distribution is effectively evolving in time. So it's not a steady state distribution, where the power law of this function S is the power law that I just described. And then you can compute what are these alpha and beta exponents analytically. So we can again use kinetic theory to find the scaling exponents. So basically what you have to do is plug in these ansatz for scaling into kinetic theory and essentially do a balancing of the time scales between the right-hand side and the left-hand side. So the way we can do that, for example, is let's assume that I believe that this is true. So when I take derivative, time derivative, what I will get that the left-hand side of kinetic theory will scale as alpha minus 1. Again, let's assume that n is much larger than 1. So let's do just some cheap scaling, some dimensional analysis of what would go on the right-hand side of kinetic theory. So let's see. So let me just write the terms. So on the right-hand side, I would have so I will implement the momentum conservation. So I will kill one of the integrals with momentum. So I will have two integrals of momentum to the dimension d. This has no scaling, so I will have a delta function of energy. And then I have n cubed terms. So the right-hand side will scale as, let's see, so there would be n cubed will scale as t to the 3 alpha. Then I want to add a t to the beta on the integral, so I will have t minus d beta. And then I have 1 over energy, so this would scale as minus 2 beta. So essentially, the only thing I did is I plug in the ansatz that I believe would be true in kinetic theory, and I do scaling of the temporal dependence of the left-hand side and the right-hand side. And this will give me a condition, which is basically 2 t minus 1 beta minus 2 alpha equals 1. So this gives me a relation between alpha and beta that needs to be true if based on kinetic theory or kinetic equations. And then I need a second relation between alpha and beta to close the equations. And here what I can use is conservation laws. So for example, if I'm looking in the infrared regime, I can assume that particle numbers get conserved. So in the infrared, I will assume conservation of particle number. So here I will have t to the b d minus alpha. And this has to be t to the 0. So this has to be a conserved quantity. So this will give me a second relation for closing this equation, which is alpha equals. So now you can solve these two linear equations, and you can find what are the spatial temporal scaling exponents in the infrared regime. Or alternatively, if you are looking towards the UV degrees of freedom, you can assume that there's energy conservation. So this is K. Again, I plug in the ansatz that I propose. And this will give me plus 2d minus alpha. So far, so good. So is it clear? Here what I'm trying to find is essentially the ratio, the scaling ansatz. And depending on what basically what length scale I'm looking into the system, I will have to assume whether there's particle number conservation or energy conservation. And you will find different relations, which you can use to close the equations and find alpha and beta. And this is basically the end of the story for a Bose gas when you are in this first case 1 regime, where you, again, let me remind you, essentially what you are doing is you are pumping energy at you are pumping a sufficiently large density of energy such that you have almost weakly interacting particles. And again, using just plain kinetic theory, we found that there are universal scaling regimes at different wave vectors and some prethermal scale. Then you may ask what happens if energy is not sufficiently large. We mentioned that the system will start condensing. So for example, at some longer scales, once enough particles will start moving towards the infrared, you will start forming a condensate. You can also use kinetic theory in that case. The key difference would be that you need to renormalize kinetic energies and interaction terms. In particular, when you have a condensate, now the fluctuations have linear dispersion. These are the Goldstone modes of the order parameter. And you will get that interactions also depend on wave vector. In fact, I wrote a few problem sets, a few problems where this would be one of the examples where you have to consider kinetic theory in the presence of a condensate. Actually, how do I share problem sets? Okay, good. No, yes. Okay. Okay. So I don't know, is there any questions about this kinetic theory? No? So let me show you now a couple of examples, both numerical and experimental. So let me start with some numerical examples.
Sorry, I have a question.
Yeah.
Just to be sure that I understood,
Yeah.
here you were essentially showing that alpha and beta are momentum dependent, as you were pointing out before, because these relations don't look to me that could be satisfied all at once, like this alpha and beta.
Correct. So good. Yes. So if that didn't come out, yes. So basically, this relation could be satisfied always because it comes from kinetic theory. So it doesn't matter which scale you are looking at. But then these are two contradictory. You cannot satisfy them at the same time. Perfect. Then which one is true? Well, it depends on what length scale you are looking at the system. If you're looking in the infrared, it would be the first one. If you're looking at the UV, you would use the other one. And from there, you can find alpha and beta.
Thank you.
So let me show you a couple of examples. So these are numerics. So essentially, this is exactly the same example I just described. This was done in the group by Asier Pinheiro Orioli in the group of Burgess. So essentially, let's focus first on the inset. The inset is basically the unrescaled distribution function, so it's a function of time. So what you see as a step function. So here, rather than starting like a delta function, like I assume at the beginning, they start from a step function, where they essentially assume a flat distribution of particles up to some finite energy, and then they cut off. Of course, this is not a thermal distribution, so the system will evolve until you reach thermal equilibrium, and what you can see is that this is what you would naively expect. You will see that particles will try to cascade into smaller and smaller momenta. You will start occupying. So here the red one is the shorter time scales, and then you start growing, and particles start occupying the lower energy states. So in principle, if you look at this figure, nothing interesting. Well, it's kind of what you would expect, but if I rescale it, and here they use precisely the scaling exponents that I used to rescale. This is the t to the beta in the x-axis, so this is the rescale momentum. So they are rescaling in this form, and they are normalizing the y-axis with the alpha parameter, so they are moving this alpha here. So when you see it in the rescale form, you see essentially that all curves collapse on top of each other. So there's a universal power law, and there's universal spatial temporal scaling. Again, I remind you here there's no drive. So here you're not driving, it's not the situation. This is only a prethermal regime. You're not driving the system at any scale, it's just completely isolated, and you can still see that you can clearly see the power loss, and you can clearly see the spatial temporal scaling. In this work, you can also find what happens with the condensate. As soon as particles start trickling down to lower and lower energy, they start condensing. The condensate also scales. You enter into a second temporal regime. Somebody asked a while ago, this one, about experiments. Actually, there were a lot of experiments, maybe 5 years ago. There were a bunch of papers in the group of Oberthaler and Schmidtmeyer in Germany, also by Hatzi Babik in Cambridge, where they essentially observed in various classes of systems. So it's not just, some of these systems were one-dimensional, other ones were two-dimensional systems. They observe in very different frameworks of very different platforms, this universal scaling and route to equilibrium. So currently there are lots of experiments trying to understand and classify, characterize this universality out of equilibrium. Let me just mention the last case that I discussed at the beginning of the class or at the beginning of the lecture, which is you could also initialize the system. So I'm not going to describe it in detail, but you can initialize the system, for example, by rotating a condensate. So these are numerical simulations. By rotating a condensate, and what you would start forming is a dense network of topological defects, basically vortices in 3 dimensions. And if the density is sufficiently large, vortices will start entangling with each other. Entangling, intertwining, and not entangling in the quantum sense, but in the classical sense. And in these cases, what you can also find is that there's another scaling to the problem where there's a different scaling exponent. In particular, in around 2010, people were very excited about this. To give you a little bit of context, they were very excited about this situation because basically the scaling exponents that you see in this highly intertwined a vortex regime matches the scaling exponent found by Kolmogorov in hydrodynamic turbulence. So people were interested in studying actual turbulence in a classical system by using this quantum turbulence of vortices, just because the exponents, so there were hints that the dynamics is governed by very similar type of processes. But that is, I think this is the last example, yeah. So this is the last example. Again, bottom line of my talk, even when you consider one Hamiltonian, there's no such thing as one pathway to thermalization. There are multiple ways, multiple regimes, multiple relevant degrees of freedom that could govern different time scales and different length scales. Next lecture, I will start focusing on a different type of system, which is spin systems. But the idea is that I will be using essentially the same type of mindset of asking, okay, let's assume I initialize my system in an excited state. What are the relevant degrees of freedom that will constrain thermalization, and how do I write scaling laws that would describe these long-lived prethermal regimes? And in the third lecture, I will also describe a different type of system, which is are fractonic fluids, where you have other type of constraints, which are kinematic constraint in dynamics. But that is as far as it goes for today. Thank you.
Cool. So thank you so much, Joaquin. Are there questions separating us from the coffee break? Formulated like that, you don't want to ask questions, right? Good. If not, let's reconvene in half an hour for Salvatio's talk. Thanks again.